afternoon, ladies and gentlemen. I will be speaking about two geophysical case studies, and will try to make some conclusions, some mathematical extractions from these studies. Excuse me. The Sun-Earth electromagnetic interaction system is one of the most complex systems in the Earth sciences. Nowadays, it is under a continuous intent monitoring using modern Earth surface observation networks, research satellites, and solar observation systems. The goal of the monitoring is fundamental studies of Earth's magnetic field, as well as important practical navigation and safety problems. Space weather events, such as strong magnetic storms, can produce significant economic damage, especially in the polar regions of the globe. There is a lot of system analysis in the geomagnetic studies. Excuse me. The surface magnetic observations are conducted by international observation system called INTERMAGNET. That system runs global network of full-scale, highest quality observatories. It includes about 120 observatories in all over the world that you see on this slide. Due to the Earth's magnetic structure, it is especially important to have enough observatories close to magnetic poles and on the equator. INTERMAGNET carries out the Sun-Earth electromagnetic interaction system monitoring on the surface of our planet. This system is a voluntary union of national observatories. The funding of the system comes from national sources. There is no centralized funding in the system. This makes system analysis in geomagnetism really appropriate and applicable, because it's not only different technical systems, technical observatories. It is also different nations and different mechanisms of fundings that are used together. Indeed, national geomagnetic observation networks are important subsystems that should be studied as a part of the complex intermag system. By red and orange, I mark the observatories that belong to joint Russian-Ukrainian intermagnet network, and this is one of the numerous subsystems of INTERMAGNET. The red and orange subsystem operates numerous observatories with a data center in Moscow in my institute. Regardless some political problems between Russia and the Ukraine, this network works perfectly, and both governments continue to fund it. Regardless, yes, I come to the next slide. Magnetic measurements in the ionosphere. The monitoring of Earth's magnetic field in the ionosphere, which starts from 80 kilometers up to 600 kilometers, is provided by magnetic satellites. In 2013, the first constellation of 3 satellites for simultaneous magnetic measurements was launched by the European Space Agency, ESA, using the Russian rocket Rokot. Important magnetic satellite missions before were successfully implemented by US NASA, Denmark, Germany, and Germany. These three satellites you see in the bottom left part of the slide. Apparent system analysis geomagnetic problem of today is to reconcile surface and space magnetic field observations. The data produced by these continuous observations create numerous derivative systems of the data acquisition, storage, management, retrieval, and data mining. The system as a whole, as well as above subsystems, are run by the 5 geomagnetic information nodes located in the USA, Canada, France, Great Britain, and Japan. In addition, there are numerous national geomag centers that assist the 5 principal ones in the above operations and studies, one of which we have in Moscow that I showed you a couple of slides before. Each of the centers does data mining to extract knowledge from the data. A big deal of data mining is systems analysis. We can also put the letter upside down and say that data mining is a part of systems analysis. Indeed, the centers do many other types of system analysis operations rather than data mining. This system analysis, which is done in those geophysical, geomagnetic data nodes, has several operations that can be considered and that are considered in our work as the part of system analysis. And here at this slide, I listed those operations. Another complex geophysical system deals with seismic zoning of tectonically active mountain countries. The goal of this systems analysis is to identify the zones where epicenters of strong earthquakes may occur. The system analysis method is generating pattern recognition systems with further integration of the gained knowledge into a knowledge base, joined for the whole set of applied algorithms. As a system analysis method, the recently created fuzzy clustering and zoning recognition system, which we call FCAZ, and several authors of this system are now here in this hall, occurred to be applicable in different geological regions located on different continents. Moreover, the notion of strong earthquakes can change from the region to region. On the slide, you can see the earthquake-prone areas recognized by moderate events in Caucasus, Russia. This is the slide in the right bottom part of the slide. And here the threshold of what we call strong earthquakes is quite low. It is magnitude 5, that we speak here about moderate earthquakes, in fact. And we have really strong events in California. This is left upper part of the slide. And here, the earthquakes are stronger than magnitude 6.5. Both results were obtained by FCAZ. Naturally, different sets of free parameters were used in these two regions. However, that was exactly the same approach. It was not only methodological approach that was the same, it was equal algorithm. Just the tuning of the algorithm was changed. So we observe here what one of the previous speakers called invariancy of this procedure. I agree that this is an important feature of a system analysis algorithm. In the same way, FCAZ is applicable to recognize areas prone to real natural disasters, such as earthquakes with magnitude bigger than 7 3/4. Such area in the mountain belt of the Andes are shown on this slide by green and red contours. Black dots are the strongest known earthquake epicenters with such magnitude, stronger than 7 3/4. And you see that the result is coherent. It is in well correspondence with what we gain from existing earthquake catalog concerning strong earthquakes. FCAZ is a recognition system which is based on clustering. The location of the strongest earthquakes, black dots, in the earthquake catalog of South America are not used for learning, since there is no direct learning in the FCAZ recognition procedure. Their good coincidence with the recognized dangerous zones is an important argument for reliability of the results presented on the slide. Furthermore, two strongest earthquakes occurred recently on the border of Chile and Peru in 2014, and in the central Chile in 2015, are marked on the slide by correspondingly yellow and blue stars. Those two epicenters were not known at all once the study was over, once the results were already published. And the INSS catalog that was used to implement the study is over in 2010. Thus, in this way, we possessed material for really pure examination. Apparently, both epicenters marked by blue and yellow stars are located in complete coincidence with the recognized earthquake-prone areas. Thus, we have independent confirmation of reliability of the FCAZ recognition in most seismically hazardous zone in the Andes. And in addition, we again confirmed that this model, this systems analysis approach, has a big deal of invariancy. It is invariant to the level of the seismic danger under consideration. Let's try to list the lessons learned. Let's try to list common system analysis features in the above magnetic and seismological studies. Among them are independent usage of different types of the recognition objects. For instance, in the problem of earthquake-prone areas, it can be segments of tectonic faults. intersections of morphostructural lineaments, disjunctive nodes, weak earthquake epicenters, some other types of objects as well, such as the plane squares of the 2D grid. It is modeling, the second point is that modeling using various geological and geophysical description of the objects. In the magnetic problem, this variety is confirmed by the, for example, the diverse features of the objects depicted on the basis of full-scale magnetic observatories. Third point is that pattern recognition from the point of view of different algorithmical platforms, including classification with learning and clustering. So the study, the pattern recognition, was implemented using several platforms. This is what I mean, and we come to somehow well-coordinated result. The fourth point is that the composition of the studied complex system into sequence of subsystems to proceed with independent system analysis studies of the complex subsystems. Here, I mean that many speakers this morning stated that system analysis is very much the analysis of the interaction between the parts of the system. Very much so, it's of course the case. But in addition, we have been able to study the subsystems we have efficiently independently. So we should construct the model of interaction between the parts once we already described quite well enough the subsystems we want to study. This is very close to what the first speaker of our session said when he was speaking about the importance to recognize the boundaries that differ the system we study from the rest of the environment. This is exactly what I mean by this state. And finally, the fifth point is that joint knowledge base should be is constructed by integrating the results. In other words, we should be able to integrate the knowledge bases obtained for the subsystems into one system. In other words, that is the instrument to study this interaction between the parts of the system. Starting from this point, let's try to list common system analysis features in the geomagnetic and seismological problem, which we consider as best practices in applied system analysis as far as geophysics is concerned. Those common system analysis features in these two problems are, first, usage of independent types of relevant recognition objects, modeling various geophysical attribute descriptions of the objects. In the magnetic problem, it is, for example, diverse features of the objects defined on the basis of full-scale intermagnet observations. Third point, independent usage of different algorithmical recognition platforms, including remote sensing classification with learning and objective classification clustering. The fourth point, natural decomposition of the complex systems under consideration, into sequence of subsystems to proceed with independent system analysis study of complex subsystems. Constructions of joint knowledge base that integrates the knowledge received from the data by the whole variety of above methods. The next step is to formalize those common system analysis features. Consequently, we try to make our conclusions more and more mathematical. We want to describe them in more strict mathematical terms. So the two important lessons learned from what I was speaking about is two features represented on these slides. The first one is multi-validness of this approach. Actually, this approach that we call FCAZ, it is multi-valid. The second feature, I call it decomposability and componentness. This is what I was already said. This is ability to decompose it into particular problems that, mathematically speaking, you can write down as the direct sum of operators. And then once you did this independent studies, you come up with an integral study. You start to study the interaction of the parts of the system. The third feature is integrability. And the fourth feature is reproducibility. That means that if we come back and want to continue our recognition, we should receive the same thing, doing the same operations. This is not always the case in applied study. Integrability of the knowledge base is one of the most important stages of the system analysis approach in this case. What this integral means is a part of a special mathematical study. Apparently, it is not neither Lebesgue or nor Riemann-Darboux integral. A hope is that algebra of databases can help to construct strict notion of such integral. I raise a question to myself: what is system analysis and what is not, as far as these two examples or similar examples are concerned? And my impression is that yes, it is system analysis if an applied problem, complex system X, is studied by several system analysis methods born outside a particular discipline, and their results are integrated into joint system analysis knowledge base. Second, significant added value can be provided to a particular scientific discipline through this joint knowledge base. And no, it is not system analysis if a problem is studied by just one method born inside a particular discipline, by the knowledge, and the knowledge base is fully constructed by the results of this unique approach. Consequently, small or no added value is provided, since the level of knowledge inside the particular discipline is a priori higher than one brought by system analysis from the outside. My conclusion is that system analysis is becoming more and more important, and we are on the stage when mathematical formalization is needed for systems analysis. It should become in its methodological, theoretical part, a mathematical discipline, or at least be very seriously mathematized. Mathematical constructions such as fields, rings, groups, semi-groups, linear spaces, Boolean algebra have its own strict and unique axiomatics. But system analysis doesn't. I think this is a challenge. Methodologically speaking, this is an important challenge, and maybe more pure mathematicians have to be involved in that. Thank you very much.